Good morning, everyone. It's time for the Tuesday morning EasyPower refresher series. Welcome to the discussion. I'm Jim Chastain with the support group in EasyPower. And as more companies begin to understand the safety hazard, which is arc flash, even more companies are beginning to understand the benefits of being more involved in the arc flash assessment itself. So the focus of the next 30 minutes is how to improve the quality of that involvement. But I'd like to start with a couple poll questions and get some feedback, if you would please. Answer kind of give us an indication of how many arc flash studies you've been involved in or your team has been involved in. And it'll kind of help dial in the direction we're kind of headed with some of these details. And so it looks like we're not working with a total novice group, which is fine, because most of the information we're going to be covering, I think, can be utilized by seasoned groups, both in a maintenance area and a consulting organization. And so based upon your experience in conducting studies, where do you see areas that can be most improved upon? And again, what I'm planning to do is essentially address these with a series of recommendations and emphasizing the features that we have in EasyPower. So again, I appreciate the feedback, and certainly it's just a matter of getting some bearing on who's kind of joining us this morning. So here's what we're dealing with, and it looks like everyone's having some common issues. And again, I welcome everyone to the discussion, so let's kind of jump into this. The industry continues to see changes in NFPA 70E in the form of specific direction and tighter guidelines. And at least in my opinion, one reason for the elevated government involvement in this area of arc flash is the resistance and pushback from companies when it comes to these measures crafted to make a safer work environment. Well, the worst part is there's a lack of understanding, a continued lack of understanding of the hazards by the very people whose safety is at risk. So it's true, the cost of an arc flash hazard assessment can be reduced by using EasyPower to complete some parts of the process yourself. It's also fair to state that the EasyPower tools will not make you a power systems engineer. But let me also state just as firmly that EasyPower tools will make it much easier to communicate with power system engineering resources that you may already have. So for consultants in the audience, this list should be considered as a path to improve the value proposition you offer to your client base by including their electrical maintenance team in the arc flash hazard assessment study. So what I plan to cover are 4 basic areas, and I'm sure there's much more material than I can cover in 30 minutes, so I may have to pick up some of this discussion in a later refresher series. But the areas I'm going to touch on are how to improve data collection procedures, how to utilize EasyPower features to spot missing data, identify problem areas as you go through the process of both the collections and analysis, and then a recommendation to get expert review of the results, especially if this is your very first study. Now, the first 2 steps or procedures are basically involved in the collection and modeling. Next week, we will cover, next month, we will conduct a 4-part series of a more in-depth discussion of what the process involves of doing the complete study. And what you're going to hear me say is that the time spent to do data collection and modeling frequently amounts to 45 to 55% of the overall effort required to do a complete study. So this is the area where the maintenance team can contribute most as far as data collection and modeling, and so it makes sense to optimize these procedures as much as possible. In Lean Six Sigma parlance, this approach is called design of experiment, or DOE, and it makes so much sense that it doesn't really take that long to get the idea across. So first thing I want to point out is that in preparation for especially your first study, but certainly as a refresher if it's been a while since you've gone through the process, I recommend 2 reference procedures or 2 reference documents that I'll show in just a second. And when we get into the tools that are available from the EasyPower website for free. One is Notes on Data Collection, and the other is Practical Solution Guide for Arc Flash Hazards. Both of these are textbook step-by-step instructions on what data that needs to be collected and how extensive the details of that data need to be and why. So then with your team, understand what EasyPower does and design an exercise that basically starts small, that doesn't just jump out and try to do everything at one time on your complete system. Make sure that that small exercise produces the results that you're expecting or need, and then with the team discuss, was it a shortcoming in the data collection process that we missed the boat, or is it a feature of the modeling, building the one-line diagram that we fell short, and how can those be improved? Improve that procedure, adjust that procedure, verify that it's going to produce the results you want, and then go large, if you will. The point I really want to make is the fact that especially in these initial stages, this is a real learning opportunity for the whole team. And it doesn't just fall on the shoulders of the person who's assigned to manage the project or do the modeling. So for instance, if this is my typical system, which is fairly complex in terms of the drawing and levels of voltages and protective devices, and as simple as we make it look to draw the one-line diagram, it's still, I think, too much of a chunk or to bite off at one time. So let me jump into the tools and let me show you what I'm talking about. And as I do that, let me go to this reference material I'm saying is available on the EasyPower website. So the first is Data Collection for Arc Flash Hazard Study. This is literally the notes that we provide when people take a data collection class from us. And these are available both for download, or you can contact me or sales@easypower.com and request this document free of any cost. Secondarily, and even more strongly, I suggest that you download, because this is much too large of a document to email, the Arc Flash Reference Guide, which is entitled Practical Solution Guide to Arc Flash Hazards. It's been updated to the NFPA 70E 2015 standards, and it is quite literally a step-by-step guide on how to go through the use of EasyPower tools in conducting a arc flash study. All right, so as we were kind of discussing, if my system ends up being too large, whether it's too large or not, I still recommend starting with very simple examples. And so, like I say, even as simple as we make it look to draw this one-line diagram, it's too much to try to tackle at one time if this is your very first rodeo. So what I would suggest is pick out a portion of your one line that takes you all the way from the utility to the lowest point in the system that needs modeling in terms of voltage, and if you want to call it that, the most remote load. So what that might look like, at least in something that I would put together, is essentially a straight line with all the interfaces between utility and the load I'm trying to label. So in this case, we know that we want to be able to label all of our 208 volt panels, some of which go through multiple stages of step-down transformers and protective devices and disconnect switches. Now, as I draw this, again, drawing the one line is relatively straightforward, you'll notice that I seem to have everything in line, and what most often happens on a first-time event, and this is the case whether you have an extremely complex system or a modest system, so I endorse starting modest first just so you don't spend a lot of time and then have to redo it later. I changed focus from the database editor, which allowed me to draw the one-line diagram, to the short-circuit focus, and then I fault the buses. And what I'm looking for here is a half-cycle, three-phase fault. As I fault the buses, you can see I get some nice colors and some nice numbers which tell me short-circuit currents, which at first blush all seems adequate. And then when I go to calculate arc flash incident energy, nothing happens. Okay, well, Jim said I'd see something here. Next thing is to call TechSupport. Wrong. The next thing is to understand what the tools allow us to do by looking at the system. So that step involves arranging the icon that's called Arranging for Arc Flash Analysis. And as I do that, this shows me the one-line diagram and all the calculations that are going into the arc flash incident energy in terms of how the IEEE 1584 model is applied. And what we see is nothing. But the clue that we're looking for is there's no valid trip device found upstream. As I go back to database editor, and I'm not going to change anything just yet, as I go back to the database editor, I tell myself, well, I got a fuse here. Why isn't that working? Even if I don't have a fuse, what I recommend is starting by putting a fuse in the system and making sure that it's fleshed out. In this case, I generally use an AB chance because it's medium voltage, a fuse link, Model T, 10 amps. What that allows me to do is go in, short circuit focus, fault the buses. Now I see some results. Now I go back and look at my arc flash hazard report. And what I'm looking for is the fact that every time there's a calculation, I see that the fuse was a protective device in play. The bottom line is, it's all about time. And whatever's controlling the arcing time, which is what this model is trying to calculate, is where we need to have our most careful attention to detail. So at that point, I realize now I don't have any of my protective devices, in this case other than the fuse, filled in. So I need to go back to the database editor. I need to then look at each of the elements. Now again, I'm still in my very simplistic mindset. I need to look at, I expect to see some protective devices in this panel. I see some protective devices down here. So the question is, why aren't they being picked up by the system? And again, this goes back to the mechanics of EasyPower, and we'll get into other clues or other ways to check out this deficiency. All right, so that's a real quick step in terms of, okay, I need to go back and refocus. Now, as I do this, was the deficiency in my data collection? Did I not collect this data when we went through my initial test? Or was it I just wasn't astute enough to do the data entry when I looked at the details on this particular fuse? In EasyPower, what we're looking to do is fill in the first 2 to 3 tabs of each data dialog box, and that's sufficient to deal with short circuit and arc flash calculations. All right, so let's, and again, as I start to learn and grow and understand better what's going on behind the scenes, I want to discuss with the whole team basically what that involves and make sure that they understand, because that's where I think there's this added value in training. They understand the reason that we fell short, at least on the first pass, is we didn't have the details on the fuse. We didn't have the details on time limitation for any of the calculations. All right. So at this point, my next step is to use EasyPower utilities to prevent mistakes and find issues still in the data collection and modeling process. So at this point, I've collected data. I think I've entered it in my one-line diagram, and so I want to see if there's any gross errors or deficiencies, at least in my entry of the data. Built into the tool is a utility called Database Browser. Right now I'm in Database Edit. I'm going to go to File, Database, and by default it shows me the browser. On this first tab, which if you look at the bottom, I'm in the Summary tab, this shows me a count of all the different elements that I have in this particular system. Now, just as a point of note, if I have a very complex system and I only left click and drag to select a portion of it, when I go back to my database editor, you'll see it only picks up that portion that I've selected, and so I can isolate, even in a very large drawing, the subsystems or the elements that I'm looking for. Now, when I go back to the whole system, look at the database browser, let's see what it tells me. First of all, as I go through the tabs along the bottom of the screen, I can isolate the listing of every element grouping, and by utilizing the Report Configuration tab at the top, I can show the default settings, which gives me a copious amount of data, which is the columns in the database. I can also modify this and eliminate extra columns that I may or may not be using. But again, that's something that is personal preference. And when I get to, well, so while I'm on buses, let's kind of just take a step there. One of the things that we kind of overlook and don't emphasize that much is that one of the criteria, or one of the things we're trying to determine as we're doing a study, not only is what the arc flash incident energy is, but whether the equipment at every point in our system can withstand the worst case fault, the worst case surge that it may ever see. And that is referred to as equipment duty. For that purpose, we need to utilize, or we need to have listed, the manufacturer's guaranteed rating for that piece of equipment. So just looking here at my bus listings, I can see I have a significant deficiency just in the interrupt rating that may be listed on the equipment, may be part of the data sheet, but for some reason I didn't get that included when I was doing my building my one-line diagram. Now when I go to some other elements, and right now I'm just going to touch on the cables and breakers, but the same applies to every element in the system. As we look at cables, this presentation gives us a 10,000-foot view of kind of what's going on, and I can catch, as I refer to them, gross errors, where I'm looking at a part of the system, or in this case, my whole system, where I have a majority of the cables at 350 kcmil or larger, and all of a sudden I have a 480 volt bus that has some sort of a load, and I have only number 4 AWG cable going out to it, and worst case it's 500 feet. So the question is, okay, did I make a typo? Did I miss the boat? Was there more conductors per phase? Something seems unclear about that particular choice. Likewise, here's another place where I didn't put the length for some reason, and you'll notice that the tool wasn't able to fill in the details of the impedance information that it needs. One of the advantages of using the database browser is that once I've located that type of situation, I can double click on the ID name. It will take me to the data dialog box, and sure enough I can see in this particular case it was a matter of not recording the length, so I can enter the length at this point. Now even as I do that, it's telling me, hey, it's really not complete. Do you really want to close the dialog box at this point? Even if I ignore that warning, you can see it goes back, reflects a change in my length entry, but it still hasn't calculated the impedances that are needed by the tool. So pay heed to the warnings as the as you go through the data entry on each of the dialog boxes. Okay, so that's cables. The other one is going to be that's fairly along the same lines as far as useful feedback and kind of glancing as to what's going on at the 3,000 foot. I've selected the low voltage breakers. I'm going to go look in at my equipment protective device settings, select that display, and now I can see just at one fell swoop, I have a lot of molded case circuit breakers, which I wouldn't expect to see long-term pickup settings, but on my low voltage power breakers, I would expect to see entries in these areas. Now that may or may not be an error, but I want to verify that we're using the right settings before I go any further. Likewise, the tool is also showing in this case we have maintenance mode available on this particular breaker. I know from just tribal knowledge and where we've worked on the systems in the past, at least one of these other buses should have maintenance mode available, and I need to kind of research why that wasn't picked up in my data entry cycle. Okay, so that kind of covers database browser. Same thing, same type of error checking applies when I'm looking at panels and motor control centers. Again, the tool, I want to make sure I'm completing each of these stages, and part of that is making sure we have the right configuration as far as how our system wiring is set up. Part of the tab, the incoming tab, is to describe what type of protective device I have on this particular panel. If I have a breaker, then I need to have, I control the description of that breaker with incoming device settings. And this is handled just like any other circuit breaker, low voltage circuit breaker in the library, and I want to fill out the same amount of information. Here I've described a generic part number. Clearly, if we're doing a study that has existing breakers, I need to have a manufacturer, and once I've found that, then I want to go in and hit the calculate button, make sure that a number comes up here because this comes straight off the manufacturer's data sheet, and then finally I go to the phase strip and pick out the size and trip settings for that particular breaker. Now, even as I complete the entries for all the loads, and in my description of the loads in this panel, I would make entries under the left side and the right side, and I'm going to have some description of my protective devices internally. Once I've completed all those load settings, I want to come to the Summary tab, calculate the downstream load, and it's going to update any sub-panels that are involved. And this is going to give me a total estimate of what the average loading or typical loading is based upon whatever duty factor I've set or percent loading scale factor I've set for this particular panel. Then as I try to close it, if I've made a mistake here, and it looks like I have, I set my main breaker up for a 15 amp setting, and yet the loads in the equipment shows a 300 amp. So there's clearly a disconnect here, and the tool's trying to give me a chance to redeem myself. So again, pay heed as these kind of mistakes are noted. Okay, so that applies to, and it applies as far as that goes, even when I've drawn a bus as a discrete bus, a standalone bus. One of the trade-offs is I probably need to do the entry here because I haven't described a specific manufacturer. And again, this goes to the equipment duty rating for this this type of equipment. I can also enable the switchgear spreadsheet, which will allow me to do a downstream calculation here, and it does the comparison based upon which is designated as the main for this bus as well. Okay, so those are some properties of the EasyPower features that allow us to kind of check as we go through and verify that we're not making data entry errors along the way. Finally, when I go to change short circuit from database edit focus to short circuit focus, if there is a mistake, for instance, if I haven't adequately characterized the cable inputs, the cable contents for this particular, let's kind of do it this way. For this particular cable, it will alert me to that fact and not allow me to change focus from database editor to short circuit. And this can be done for the whole system, frankly, or just a portion of the system that I'm working on. So it'll give me a report or show and highlighted in red the mistakes I'm making here. So those are pretty much the facility, the utilities that are built into EasyPower. The final, as we do studies, because we assist customers to do arc flash studies as a support to tool owners, we very frequently, if we're involved in the data collection side of the equation, we will take voltage readings as we're going through and collecting data on the system, on any part that's powered up. What we're doing as you're building this one-line diagram is literally modeling an ideal depiction, an ideal model of what your system is. And if it is working properly, which usually when we're doing an arc flash study, we either know there's issues or we assume that the things are operating normally, then the ideal system should perform in a simulated power flow study with results that say, okay, yeah, we've got normal operations. If we have a discrepancy between the voltage levels that are measured, and in this case, the voltage levels that are predicted by the power flow study, this can indicate a problem with the way the model's been constructed. Again, whether it's either data collection or data entry is a function of where we stand, but the power flow is kind of the backup error checking to verify that we haven't made some kind of gross error. Here we're seeing that this bus has about a 20% drop in voltage, and when we took the readings, that wasn't the case in the real system. So that would make me think to go back and verify what's going on with this cable. Now you see the way I've set up the displays here, I'm not showing the cable data. That's a function of my options. If I right-click in an open area, go to my text visibility, you'll see I don't have cable data showing. If that were part of it, I might see that, okay, this cable is undersized. I'm using C350 kcmil over here and only a 4 AWG here. So it looks to me like I probably had a typo, and I'm more than likely expected to see a 4-aught, for instance. But I'd have to verify what the data was as opposed to what the data collected as opposed to what my data entry was. And so I bring this up because if you have any intention of utilizing this database in the future for more than just arc flash, this ability to kind of compare it against your actual system is literally the function of the power flow module. And for the most part, it works primarily with the data that we've collected for arc flash. All right, let me kind of jump back into my slides. So we've talked about the database browser, the data dialog box, and how certain elements do some error checking, and by all means pay heed to those. We talked about the arc flash hazard report. We didn't get into too much detail on the short circuit options. That's something clearly you want to make sure you cover when you do your power start session with the new tools. Basically, there's also a facility built into the database edit that is called Scenario Manager, which lets us set up basic configurations that may even exist on a temporary basis in our system, and the tool will automatically compare incident energy calculations and it gives us the ability to do what-if comparisons, not necessarily error checking as it is per se. So problem areas, if we're going to be highlighting problem areas and we're confident that we've completed our data collection and building the model as cleanly as possible, we would utilize the scenario manager for what-if discussions. If we're looking for miscoordination, the sequence of events utility, which is built into the coordination module, is extremely valuable in giving us a first look at whether or not we have a gross misadjustment of breakers, or if it's isolated only to one or two buses. And we'll be covering that at a later refresher. Series coordination, again, a feature built into the device library and can be utilized to make sure we have coordination potential between multi-case circuit breakers. And likewise, Smart PDA can do automated recommendations for protective device coordination. And then we talked about power flow. So then finally, the last on my list, and I apologize for coming up a little bit short on time, is especially if you're in your first stage of, or the first arc flash, it's important to get as much guidance as possible from experienced resources. And EasyPower is not the only place to go to. We have many dozens of consultants across the country that have expertise in the EasyPower tool suite and can help lead you through the process of both data collection and doing the modeling, and then would be more than happy to pick up the files at that point and do a file review and complete the arc flash study. This is something that we could do from afar. Very frequently, people will send us to a file, an EasyPower file. Okay, Jim, we think these got this completed. We've completed our study. We'd like to have an official engineering review of the results and the methodology. We would actually provide a quote based on the hourly rate and literally just charge for the time that the engineer spends on the files. At the end of that, you get a report back and a 1-hour webinar one-on-one to review what the results are and include recommendations to how to improve the process. And at that point, you know an expert's basically got your back. That completes my list. By all means, I would like to make sure you take advantage of the resources that are available on the EasyPower website. The tutorials are, several are very much in-depth on specific topics. The availability of the demo tools are both instant use and 30-day downloads. And then we have a series of biweekly technical presentations along with our refresher series. I'd like to mention also that we have regional training listed on the website. Registration's open for the July session here in Portland. We will be holding a regional training in Vancouver, BC in September, and then Dallas in October. And by all means, those of you that have an interest and a need to get into more technical knowledge, more depth and technical knowledge on harmonics and dynamic stability, we will be conducting a hands-on course in October here in Portland for that as well. By all means, you're welcome to contact TechSupport as a tool owner and in good stead as far as the maintenance. And you're welcome to contact either by email or by phone. I thank you to everyone for attending. Again, if you have suggestions for future topics, you're welcome to send emails or contact me, Jim at EasyPower.com, and I look forward to talking to you next week.